Hi there, everybody. Thanks for tuning in today. Today we're going to talk about logarithmic scales. And we've been looking at different ways that logarithms show up as we model data sets and things like that. And I just want to wrap up our conversation on uses of logarithms with this idea of a logarithmic scale. Logarithmic scales are used when there is such a great difference between values of some sort that it's hard for our brain to wrap around numbers that get so big. Okay? Our first example is going to be the Richter scale. Okay? The Richter scale is something that gives the magnitude of an earthquake, if you're familiar with that. Right? You have seismographs that measure the intensity of the vibrations in the earth. Okay? But we don't just give the intensity of the earthquake when we communicate its scale. We use a logarithmic scale to do so. So you can see on the screen here that R, as our Richter scale number, is equal to the log of I over I sub 0. Now notice this is log base 10 since the base isn't written. What are I and I sub 0? Okay. I is the intensity of the earthquake, okay, measured by graphs. Okay. I sub 0 is the intensity of a level 0 earthquake. Okay. So what we're doing is we're taking the log of how many more times intense this earthquake is. Did I write earthquake? Oh my, earthquake. There we go. That's funny. Hey, we're taking the logarithm of how many more times intense this earthquake is than a level 0 earthquake. Let me get to an example to help this make sense. Find the Richter scale magnitude of the 1999 Joshua Tree, California earthquake. So that one's known as a very intense earthquake. It had an intensity that was 12,589,254 times the intensity of a 0 level earthquake. So let's find our Richter scale value. Okay. R equals the log of, okay, now it says this 12,589,254 times the level, the intensity of that 0 level earthquake. So times, what do we call the intensity of a 0 level earthquake? I sub 0. Okay. Over, okay, take a look back right here, over I sub 0, and we can see that the I sub 0's cancel out. Okay, so we're taking the log of that 12 million number. I'm grabbing my calculator. Okay, log 12,589,254. Okay, I get about 7.1. So that would be a 7.1 on our Richter scale. Let's look at a different earthquake. And actually, let's look at two earthquakes and compare them. So here's what I want you to see. In 1960, there was an earthquake in Chile. It had a Richter scale of 9.5. In 1989, there was a San Francisco earthquake that had a Richter scale of 7.1. Okay, that's similar to that Joshua Tree earthquake just 10 years earlier. Compare the intensities of these earthquakes, right? So we see that, okay, this one in Chile was 9.5 and this one in San Francisco was 7.1. How do their intensities compare? So, okay, let's start with the Chile earthquake. Now notice we know the Richter scale is 9.5. So I'm going to say 9.5 equals the log base 10 of I over I sub 0. For the San Francisco earthquake, okay, we would have 7.1 equals the log of I over I sub 0. And what we want to do is we want to compare their intensities. So what I want to do is I want to solve each of these for I. Now, because this is a logarithm and it's log base 10, we're going to rewrite this as an exponential. 10 to the 9.5 equals I over I sub 0. Multiplying by I sub 0, we get that for the Chile earthquake. Now let's come over to do the same thing for San Francisco. 10 to the 7.1 equals I over I sub 0. So 10 to the 7.1 I sub 0 is the intensity of the San Francisco earthquake. Now, as we compare their intensities, let's do a comparison by looking at their ratio. So what I'm going to do is I'm going to take the Chile's intensity, Chile earthquake intensity, and divide it by the San Francisco earthquake's intensity. So this is going to be 10 to the 9.5 I sub 0 divided by 10 to the 7.2 I sub 0. And notice the I sub 0's cancel out. We have 10 to the 9.5 over 10 to the 7.2. What happens with exponents when we divide? Okay, well, we're going to subtract those exponents. This gives me 10 to the 2.3. Okay, and what is 10 to the 2.3? Well, 10 squared is 100, so it's bigger than 100. Okay. Putting that in my calculator, it's almost 200. Okay. It's about 199.5. So that tells me the Chile earthquake is 199.5 times the intensity of the earthquake in San Francisco. See, this is why we use Richter scales. We can say 9.5 and 7.1. We don't have to say, okay, 199.5. And by the way, that's not even the intensity of the Chile earthquake, because that's at a 9.5. Just the difference in intensities here is this 9.5 is 199.5 times more intense. That's because when we look at a log base 10, okay, each difference, okay, in the Richter scale is going to correlate to a 10 times greater value. Okay? Let's just look at that for example. Let's say an earthquake has a Richter scale of 8, okay? And another earthquake has a Richter scale of 4. See, somebody might be tempted to say, hey, this Richter scale of 8, that earthquake is twice as intense as the Richter scale of 4. But that's not true. Okay? How many more times intense is that? There's the intensity for the Richter scale 8 earthquake. Okay, are you guys okay with me skipping a few steps? That's the intensity of the 4 on the Richter scale. So how many times more intense, okay, is this one than that one? Let's divide them. 10 to the 4th, 10,000 times more intense. That's because for each level that we go up in Richter scale corresponds to being 10 times more intense. Okay? Our numbers here get so big that we use a Richter scale to draw it in to help us be more reasonable for us to communicate. But we have to remember, because here's the danger. Like I said, the danger is saying this one's twice as intense as that one. Okay? We have to know what we have for logarithmic scales, okay, and be able to think that way in powers of 10. Little fun fact, if I was in class here with you guys and we were looking at this together, I would show you the 1989 San Francisco earthquake. It actually happened during a World Series game live on TV. If you're interested in that, you can YouTube that broadcast and see that happen. Scary time for those people in San Francisco. So, what else are logarithmic scales? If I just said it's important for us to know which scales are logarithmic so we can think about them correctly, okay, we need to ask ourselves, well, what else are logarithmic scales? Okay, two more examples. One is sound, or how we measure things in decibels. Another one would be the pH scale, okay, when we talk about acidity and things like that. I don't have any examples on the pH scale, but let's talk about sound. So decibels, okay, you're probably familiar with hearing that when it comes to music or sound recordings, things like that. Decibels is a logarithmic scale to describe how loud things are based on their intensity. Now notice it has a similar look, okay, to our Richter scale, except there's a times 10 in front, okay, and then we have P over P sub 0. Okay. Example, a gunshot for a .22 rifle has an intensity that is 2.5 times 10 to the 13th times louder than the smallest audible sound. So remember how in the Richter scale, this I sub 0 is the intensity of a level 0 earthquake. I just can't believe I wrote earthquake. This P sub 0, okay, is the intensity of the smallest audible sound. That's this P sub 0. All right, so, okay, how many decibels would this be? Well, it's 10 times the log of, it's 2.5 times 10 to the 13th times the smallest audible sound. So P sub 0, so just some scientific notation, divided by P sub 0. Notice the P sub 0's cancel. This is 10 times the log of 2.5 times 10 to the 13th. If I put that in my calculator, 10 times the log, 2.5 times 10 to the 13th, I get 134.0 decibels. Okay, that's how we would report how loud that sound is. Okay. How many more times intense is this than a cat who purrs at 25 decibels? All right, so a purring cat. Okay. How many more times intense is that rifle shot than this cat purring? Well, let's set 25 decibels equal to 10 times the log of P over P sub 0, and let's solve this for P. I need to divide by 10 first. Let's rewrite as an exponential and multiply by P sub 0. All right, so that is the intensity of the sound of the cat purring. How many more times intense was that gunshot? Well, that gunshot was 2.5 times 10 to the 13th. So let's take 2.5 times 10 to the 13th P sub 0 and divide it by 10 to the 2.5 P sub 0. Now the P sub 0's cancel. Notice it's a multiplication, it's a product on the top, okay, and division on the bottom. When we multiply and divide, order doesn't matter. So I'm going to say this is 2.5 times 10 to the, okay, what do we do with exponents here when we divide? We're going to subtract to the 11.5. So we're taking the intensity of the gunshot divided by the intensity of the cat purring. And this is going to be an enormous number. Okay. I mean, this is, oops. I don't even know if my calculator is going to want to do this. There we go. It's in my calculator, I'm getting 7.9 roughly, times 10 to the 11th times more intense. Okay. That means we have to move this decimal 11 places to the right. That's how many more times intense. Now, it might be tempting to say, oh, 134 divided by 25, that's just over 5. It's just over 5 times more intense. No, that gunshot is an incredible amount of times more intense than the cat purring. This is, again, why we're using a logarithmic scale, because our numbers are so different. By the way, if you're curious on levels of noise in decibels, how things compare, here's a little chart that's kind of interesting to look at. Our top one here is painful and dangerous sounds like fireworks, gunshots, custom car stereos at full volume, jackhammers and ambulances. Those are in the 130s to 140s. It's uncomfortable things like jets, things that are very loud, all the way down to leaves rustling at 20 decibels. Okay. So again, we can't say that a jet plane is 6 times more intense than leaves rustling. We have to think about how that logarithmic scale works. And because there's that 10 in front, where did it go? Right here, it's not as simple as the Richter scale where each one represents 10 times more. There's that 10 in front, so you got to divide that over. But that's the concept. A couple other things to show you quickly regarding logarithmic scales. Things called semi-log graphs. Okay? Notice when we look at this graph, this is the graph of 2 to the n. Okay? Now 2 to the n we know is an exponential. It should be a curve. But what a logarithmic graph does is it keeps the x's the same, and we take the logarithm of the y values. This is similar to what we did on our calculator and in GeoGebra the other day, okay, when we came up with the equation of an exponential through a data set by first taking the log of the y's and seeing that that fit a line. Notice how this graph works. Notice how these lines aren't evenly spaced out. That's because as we take the log, okay, we're really condensing things down, right? So that's 1, that's 2, 3, 4, 5, 6, 7, 8, 9. Okay. And we're squishing it down vertically from growing so fast to make it to a line. Now we're at 10, okay, and then here we're going from 10 up to 100. Okay. So this is actually 20, 30, 40, 50, 60, 70, 80, 90. Sorry, I can't really fit them in there. Okay. Then we're going from 100 to 1,000. So this is 100, this is 200, 300, 400, and so on. And when we take the log of the y's, it squishes it down into a line. Those are called semi-log graphs. You can also have log-log graphs where you actually do that with both the x's and the y's. That should remind you of the power model. So I see a line here, so I know that this must be some sort of x to the n function from a power model because we're taking the log of the x's and the log of the y's. And we see how that scale that we saw vertically was interesting in the last one is the same thing horizontally here. All right. So introduction to some logarithmic scales. It's important that we understand how to interpret them, that we don't make mistakes as we compare values. Hopefully that's useful for you. Thanks for watching. I'll see you next time.